Welcome to Organic Nitrogen Compound Tutorial presented by the SHLDB with reference Cambridge International AS Chemistry by Lori Ryan and Roger Norris. So we are going to start with the learning outcome of organic nitrogen compound chapter. So you should be able to describe the formation of alkyl amines, halogenoalkenes, or reduction of amides using lithium ammonium tetrahydride or all that. So we have described and explained the basicity of amines and a relative basicity of ammonia, ethylamine, and phenylamine. Describe the reaction of phenylamine with aqueous bromine with nitrous acid to give the diazonium salt, and phenol followed by coupling of benzene, diazonium chloride, and phenol to make a dye. Describe the formation of amides from the reaction of that and the hydrolysis of amides. Describe the acid-base properties of all that. Describe the formation of peptide bonds and describe a simple process with electrolysis. So now let's start electrophoresis. So now we start with amines. And to start with amines, you need to know the distinction of different amines. We first know that the physical property of amines is that amines are going to have hydrogen. They can have hydrogen bonding. This is why amines are going to have a high boiling point, and they have hydrogen bonding because of the condition of hydrogen bonding. I've initially told you in the introduction of chemistry. I've said that there is hydrogen bonding when hydrogen is bonded to a highly electronegative atom, and there exists another molecule having a highly electronegative atom with lone pair of electrons. So you see that nitrogen is highly electronegative, and hydrogen also has a lone pair of electrons, and hydrogen is also bonded to it. So it fulfills all the conditions of hydrogen bonding. That's why amines have hydrogen bonding. So now we have classes of amines. There are three main classes of amines. You have primary amines, secondary, and tertiary amines. So now for primary amines, you have the NH2 group, or the amine group is going to be attached to the carbon atom having two hydrogen atoms attached to it. For secondary amines, it's going to be attached to carbon atom that has so in this case, for secondary amine, for primary amine, you see that hydrogen is going to be attached. For secondary amine, is going to be attached to carbon atom having only the amine here. For primary amine, there is going to be NH2 group. For primary amine, you have an NH2 group. For secondary amine, you have an NH group. You instead have NH, and for tertiary amine, only have N. Those are the different cases. So these are examples. This is a methylamine, ethylamine, propylamine. This is a secondary amine, example dimethylamine, and this is a tertiary amine, trimethylamine. So in order to name this, we need to know first the position of the main functional group. So in this case, it is methylamine. We are just calling it trimethylamine. So that's the point. So now let's visualize the basicity. Let's visualize now the basicity of amines. So now the basicity of amines. So now you need to know that amines are actually basic. So let's take this different example and visualize which one is the more basic than the other. Is it a tertiary, secondary, or a primary amine? So the point to note is that what is a base? According to Bronsted and Lowry, as you have seen in acid base, we've said that Bronsted Lowry define a base as a proton acceptor and an acid as a proton donor. So here we are trying to find if this base is going to be proton acceptor. So now you see this, we see that here you have, let's say, a primary amine. So that's a general. We have a primary amine here, methylamine. So since this is methylamine, you see that what there's a methyl group, a proton acceptor. When we say a base is a proton acceptor, it means that it is rich in electrons, such that it's going to give much more electron to the center that wish to accept those electrons. So that's according to Bronsted-Lowry. Another definition that you can use here as for a base can be using the Lewis definition of a base. Lewis definition of a base defines a base as an electron donor. So you see that in this case, you are going to find which species between primary, secondary, and tertiary amine are going to be more in donating electrons. So now we have the first case. We have methylamine. You see that this methyl group is going to give electron to the nitrogen, and then you have one group that is going to donate electron to nitrogen. So it can be, that's why it is a base because it's going to donate electrons. So it makes this N to be much more negative, and thus this N can give electron to the acid. So that's why the primary amine is basic. Now the second point here, in the case of dimethylamine, you have two methyl group attached to N. In this case, you have one methyl group that is going to give electron, another methyl group is going to give electron. So you see that in this case, there is much more electron concentrated on the nitrogen. So it implies that the secondary amine is going to be much more basic than the primary amine, because this is much more electron donor than this case of methylamine. And then the last one, you see that nitrogen is going to be bonded to three methyl groups. So three methyl groups are going to give electron, and going to cause much more electron on nitrogen, so much more electron donor ability. So the tertiary amine are much more basic than secondary amine, which are much more basic than the primary amines. So now let's see basicity of, so we have seen already the basicity. So we can also say that when comparing that, we see we have primary amines. The next one is that primary amines are going to be more basic than ammonia, and ammonia is going to be more basic than phenylamine, which are the weakest. So now let's see the formation of amines. So now in the formation of amines, we have how do we make amines. We can make amines from halogenoalkane by binding halogenoalkane like that. So this hydrogen are going to we are going to the loss of hydrogen and loss of bromine. So this is going to be formed. Ethylamine is going to be formed. The next point is a bromomethane and ethanol and a cyanide. So this bromide can be lost and can be replaced by the cyanide ion. So you are going to have ethanol nitride, ethane nitride, so or just call ethane nitride. So now we have here in case now where you do the reduction of this nitride, you can have here an amine. So you first start by putting the cyanide ion, and then you have now an amine. You have now an amine when you want to when you do reduction with lithium aluminum tetrahydride in dry ether. The next point is using lithium aluminum tetrahydride on an ethanamide. So what is it going to produce? When I use an ethanamide, I use lithium aluminum tetrahydride directly, I'm going to produce ethylamine. Now phenylamine is made up of reducing. Now when you want to reduce this molecule, I've initially told you that the benzene ring increases the reducing ability of a molecule. So now to reduce the benzene ring is going to be much more difficult compared to oxidize a benzene ring, because the benzene ring increases the reducing ability. So to reduce a reducing agent, it is difficult to do so. So now in order to reduce this benzene, compared to this benzene molecule compared to this other molecule that was containing O like that, here we were using lithium aluminum tetrahydride, but in this case you are going to use instead a highly reducing agent, and that highly reducing agent is going to be tin plus concentrated hydrochloric acid, or even zinc plus concentrated hydrochloric acid. All of them are going to reduce now to produce this. So now that's the point. So I've initially let me emphasize again on this point. I've said that benzene ring increases the reducing power, so it makes the other an oxidizing species to easily oxidize benzene ring, but it makes a reduction of the of that molecule to be much more difficult. So in order to reduce that molecule, you need to use again a strong reducing agent, and in this case you cannot use lithium aluminum tetrahydride in order to do this conversion. You instead use tin plus concentrated hydrochloric acid. That's the point. So the next point is reaction with phenylamine. So reaction with phenylamine, you said that I've initially told you that the NH2 group was activatory on the benzene ring. It was causing activation of the benzene ring. So in this case, when the bromide ion is going to be coming in presence of iron tribromide, in this case you are going to have the positioning of the bromide positive ion are going to be on the ortho and the para position. So this is why you have this molecule that is going to be formed at the end, 2,4,6 tribomophenylamine. So now the next point is diazotization. So now you need to know that what this diazotization occurs when you have an amine that binds with nitrous acid. When you have any amine plus nitrous acid is going to produce the diazonium ion. So that's called diazotization. The process of formation of diazonium ion, using an amine and nitrous acid. But you need to know that what nitrous acid, when it's produced and left in air, is easily oxidized to produce nitric acid. So this is why in this reaction of an amine with nitrous acid, you do the production of nitrous acid in situ, that is sodium nitrite plus hydrochloric acid is going to produce now the nitrous acid in the milieu, and that nitrous acid in the milieu is now going to bind with the amine, in this case is phenylamine, to produce the benzene diazonium ion. So this is the benzene diazonium ion. So now the next point now is how do we do coupling reaction. So the diazotization is very important because it's used in doing a coupling reaction. Example, the diazonium ion can bind with the para position, mostly the para position of this of any aryl compound. So it's going to bind with the para position of this aryl compound to form this other compound, and these are called di. So we have an azo di here, so which is a diazonium dye, which changes in color depends on the milieu. So by using alternative compound phenol, we can make a range of brightly colored dye for compounds. So we have different color that you can produce because this bond here is having ability to absorb different light. So you can produce different light, different compound, different dye or compound that color solution by using this azonium ion, this diazonium ion. So now the next point is amino acid. The amino acid have the general formula of RCCOO, N and H here. So this is RCO, and they are respecting the corn rule. So now the next point to do is to know the formula of glycine. Glycine is given as such. For glycine, the R is going to be H. The R here is going to be H. So it's also called amino ethanoic acid. It's also called amino ethanoic acid. So this is alanine. Alanine, the R is instead going to be CH3. So that's alanine. So now we need to know how the existence of amino acid in solution. We need to know that what amino acid, unlike other compounds, are going to exist in solution as zwitter ions. Amino acid exists in solution as zwitter ions. That is, when you place this amino acid in solution, the hydrogen ion in water is going to bind to this position to form NH3, and this other part is going to release electron to produce this. So they exist all in form of zwitter ions. So since they exist all in form in solution as zwitter ion, it implies that what if you add acid to this molecule, acid is going to bind at this position, and thus the amino acid is going to be much more positive. If you add acid to this molecule, you need to know that what amino acid, when they are at a neutral pH called the isoelectric pH, they are not movable. At the isoelectric pH of each amino acid, they are not movable. That is, they exist at a complete positive and negative, as positive and negative of each side. You see that when you have positive here and negative here, and we place electric current, there is equal attraction to both sides of the electric pole. So this is not going to be conducting current. It's not going to move when current is going to be placed in solution. But now when you place hydrogen ion in solution, you realize that what is going to exist much more as positive ion because of the NH3. Since it exists much more of as positive ion, this is going to move toward the cathode. It's going to move toward the cathode. And now the next point is when you have hydroxide ion. When you add hydroxide ion, you need to point out the fact that this hydroxide is going to bind to the H plus on this NH3 plus to produce this. So the molecule is going to be much more negative, and it's going to move now towards the anode. So now reaction of amino acid. The main reaction of amino acid is the peptide, the condensation reaction in the formation of peptide bonds. You need to know that the COO terminal of the first amino acid is going to bind with the NH2 terminal of the second amino acid to form the peptide bond, and this is how a peptide bond resembles. This peptide link is going to be C double bond O and C like that. This peptide bond actually is an amide. So now let's visualize now amide. So reaction of amide. So the reaction of amide, you have the process of making amide. So how do you make amide? You can make amide from an acid chloride. So you place ammonia. This is ammonia. You place the amide, and then you produce it from acid chloride. You can produce it from different. You can produce it from ammonia. You can produce it from primary alcohol, a secondary alcohol. You can produce from primary amine, a secondary amine, and all that. So now when you place ammonia, you are going to produce instead a primary amide. Now when you place a primary amine, you are going to produce a secondary amide with a peptide bond. In the middle, you are going to have the peptide bond, and have the names of this molecule are going to be given with respect to the side chain and the main chain. We give the first name is going to be the main chain. This molecule is having the main chain here is going to be having 4 carbon atoms. So since it's having 4 carbon atoms and it is an alkyl group here, since it has 4 carbon atoms and alkyl group, so the main chain is going to be called a butanamide. The main chain is going to be called butanamide, and now the side chain is going to be n ethyl, because at this you have the ethyl is going to be bounded at the end portion. It's going to be n ethyl. So the total name is going to be n ethyl butanamide for this molecule. So that's how we name an amide. So now the reaction, so that's how we have this reaction. That's the first reaction for production of amide. This is secondary amide, is a primary amide. So now the next point is hydrolysis of amide. You need to know that what amides are capable of being hydrolyzed, like also like the hydrolysis of acid chloride. All the derivatives of carboxylic acid are capable of being hydrolyzed to produce the corresponding acid. So you have an acid hydrolysis in presence of hydrogen ion is going to produce the carboxylic acid and is going to produce an amine. So excess of the hydrogen ion is going to produce instead the positive ion of the amine. And now we have also an alkali hydrolysis. Alkali hydrolysis produce the metallic derivative of the carboxylic acid, derivative of carboxylic acid, and it produces an amine. This amine is not going to be existing in positive form as such here. So now the next part of this chapter is going to be electrophoresis. Electrophoresis, as we have initially spoken about in case of zeta ions here, is just placing an electric current on a strip of on an electrophoretic plate having a certain solution present in it. So these are different things. You need to know that what different solutions have different ability to conduct electricity. So like example, these are amino acid having different ability to conduct electricity. We have lysine at this position. We see that lysine has 2 positive side and has only 1 negative. So since it has 2 positive and 1 negative, it's going to be much more conducted toward the anode. So lysine is going to be much more conducted toward the anode at a neutral pH of 7. So when you have a neutral pH of 7, now lysine is going to be much more conducted at the cathode because of positive at the cathode. Now you have at this other position glycine. Glycine has positive here and negative here. You see that glycine is going to be much more, is not going to be conducted, not going to move because of equal attraction and attraction on both sides of the cathode and the anode. And here you have glutamic acid. Glutamic acid has much more negative compared to positive, so it's going to be much more conducted toward the anode. So in this diagram you can visualize here, you see that lysine is going to move much more toward the positive, toward the negative side. You see that lysine is going to move towards the negative side, and this is why you have the representation A. A is going to move toward the negative side here. That's why on the ship we are going to visualize this line. This line is going to show for lysine. For glycine, glycine is going to be at the center. B is not going to move, and then you have C here is going to move toward the positive side called the anode. So that those are the different view. So from here we have seen everything involved in organic compounds, organic nitrogen compounds. So say thanks for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.